Got it? No, you're fine, you're fine. All right, everybody. Are we ready? Did y'all get that homework assignment? I sent it yesterday afternoon. I apologize, but was that?
Oh, yeah. I
you have a question? Yeah? Yeah? What, can you tell me which one it was?
Yeah, it was, let me oh, not number 19, my bad. It was number 20, and it was negative 2 times e to the 7v power.
7v?
Yeah, 7v plus 5 minus 10. If I'm saying
Wait,
that
plus
correct.
5 where? Let me see where the plus 5 was.
Right.
Okay, plus 5 up here, minus 10.
Minus 10 equals negative 17. And my question was whether you would divide first or add.
Good question. This is a real good question. So the homework assignment, if you actually did look at it, the beginning problems were pretty basic, and then they kind of built up in difficulty, this being probably the worst type that you could see. So the question is, how do we go about this, right? What do we do first? So we eventually would like to get the V out of there, right? We want the V to drop down. But the V is actually attached to all of this, right? This whole thing is in the exponent. So we're going to want to somehow drop this down, right? But to drop that down, we can't have that negative 2 that's in front. We can't have that. In addition to that, we cannot have the minus 10 on this side of the equation. So basically what I'm telling you is this. You have to try and get the thing that's being raised to a power, the e, you have to get this in everything up there, all of that, you need to get that by itself on one side of the equation. All right, once you have that by itself on one side of the equation, then you can bring in the natural log on both sides. So to do that, I have multiplication between these two. This is negative 2 times this, and then I'm subtracting 10. So I'm going to start, this is just like think of it more like a linear equation. Like if I gave you 3x minus 4 equals 10, asked you to solve this, what would you do first? You add the 4 first, right? And then you would divide by the 3. We're going to do the same thing here. I'm going to add 10 first. That gives me negative 2 e to the 7v plus 5 equals negative 17 plus 10 is negative 7. I forgot my calculator again. Now what? Divide everything by negative 2. Negative 2 here, negative 2 here. The negative 2's go away, right? So now on the left-hand side you have e raised to the 7v plus 5 equals, and then on the right-hand side that's going to be a positive number, right? Negative divided by negative is positive. What, 3.5? Okay, 3.5. All right, we have isolated the thing that's being raised to that variable power. Now we can bring the natural log in on both sides. When I bring the natural log in on the left, good things are going to happen, but I have to do natural log on the right as well, and that I will use my calculator for. But not yet, I'll do that in a second. I now want to use the property that allows me to take this whole thing and drop it to the front. And that becomes 7v plus 5. Put that in parentheses in front of times natural log of e equals natural log of 3.5. And this is 1. That's the thing you have to remember. When you have the natural log of e, it turns into a 1. So really we can just ignore it, all right? We can just ignore it, and now we have 7v plus 5 equals, okay, go ahead and do this on your calculator. Natural log of 3.5. Let's round it 2 decimal places.
1.25.
So 1.25, is that okay with everyone? Yeah? Okay, now what we're looking at here, we're back to the beginning of this class. This is a linear equation. You're just trying to solve for v, right? You're just trying to get the v by itself. So I'll subtract 5. Subtract 5. That gives me 7v equals, okay, 1.25 take away 5, you should get negative 3.75. Final step, divide by 7. V equals, we're going to get a negative answer here. What do we have? 0.53-ish, somewhere around there. There you go. That's as bad as they'll get, right there. Do we have any questions? Thank you for asking. Yeah. Do I need to clarify any of these steps? All right. Would you like me to do another one off the homework? Which one? And you want to pick one? You said yes. Yeah. Do you want? Okay. Remember, our exam is a week from today, right? In case you weren't here last time. Our next exam is on Wednesday of next week. And then we're going to, actually, I'd like to talk about a review today a little bit. And then I told you I'd give you a review before the weekend. So, and then Monday we come back, we'll do review, and then Wednesday the test. Okay, go ahead. Negative 10e. 2b. B is in boy. Minus 6 here, like that. Negative 66. There we go. All right, so again, our goal here is to try and get this by itself, right? Can we get that by itself? And the way we get that by itself is to first get rid of the other stuff. So what should I do first here? The 6, right? That negative 6, let's add 6 to both sides. It'll go away over here. I'll have negative 10e raised to the 2 minus 2b. Over here we'll have negative 60. Negative 66 plus 6 is negative 60. Now I will divide by negative 10 to get rid of that negative 10 in front of the e. We'll have e raised to the 2 minus 2b equals 6. Negative divided by negative is positive. Now I can bring in the natural log on both sides, right? So I bring in the natural log. What I do to one side, I must do to the other. On the left-hand side, this 2 minus 2b is going to drop in front. And that gives me 2 minus 2b. I put it in parentheses. Natural log e equals natural log 6. And again, the natural log of e turns into 1. So it really just goes away. And you're left with 2 minus 2b equals, calculator, natural log of 6. What is it? 1.79. Oh, I should tell y'all something. Let me finish the problem real quick though. Okay, what next? Trying to solve for b. That 2 right there subtracted on both sides. So subtract 2 goes away over here. You still have a negative 2b equals negative 0.21. Negative 0.21. And finally, divide both sides by 2. No, sorry, negative 2. Negative 2 here, divide by negative 2 here, goes away. We get b equals, what is that? Positive answer, 0.105, I believe. Okay. Is there a question?
Oh, no, I was just wondering how you got the answer in your head because do you already know it or?
I'm ignoring the decimal, and I'm saying 2 goes into 2 once, and then it doesn't go into 1, so I have to carry a 0, and then it goes in there 5 times. I'm not good at arithmetic like that.
Oh.
Most people think like math people are like human calculators. I'm not a human calculator. Yeah.
No, yeah, I was just looking at it.
Yeah. Yeah. Math is something very different than what you think it is at this level. Like, I thought math was a certain thing, and then when I started studying it more, I realized, whoa, it's not at all what I thought it was. I thought it was just like numbers and. Okay, that okay? All right, so I needed to let you all know something. I'm not going to record, so I'm going to mute myself just because I don't want to have it on video. All right. Yeah, everyone's like moving over here to this side of the room. Yes.
Has anyone ever told you kind of look like
Goofy? Goofy? Like what? The character Goofy?
Yeah, respectfully.
That's a first. That's a first. I'm recording that. I'm recording that. Thank you, though. Yes. Yeah. Do you have a request? Okay, can you read it to me? Ready? 6E. Raised.
Minus 4k minus 10 and then minus 4
Equals 63 like that? Did I do that right? Okay. No, I've had people tell me that there's I guess some character from The Walking Dead or something like that.
Dean Morgan, yeah.
Yeah, I never watched The Walking Dead, so I have no idea who he is or something, you know. But I've heard that before, but you know, not Goofy, not Goofy though. Not really. Let's go. It's gonna be fun now. Yeah, I mean, whatever. Everyone sees what they want to see. Some people see Goofy, some people see that, some people, right? Okay, so let's get to this, yes? All right, so trying to isolate the thing that's being raised to the power, right? So first things first, I see a 6 here attached with multiplication. I see a minus 4. I'm going to get rid of the minus 4 first. Add 4 to both sides. Goes away here. 6e to the negative 4k minus 10. I can't wait to tell my wife.
About the Goofy thing?
Yeah, she's going to love it. She's going to love it. You won't believe it. All right, divide both sides by 6. Right, divide both sides by 6, yes?
You sound like Nicolas Cage. I don't
That I've heard before as well. That I've heard before as well. I've heard that more than anything I've ever heard. Yep, I've heard that. Okay, so dividing by 6, are we good? Okay. So we got e to the negative 4k minus 10 equals, all right, that's going to be a decimal. It's going to be what, 1.1, or sorry, not 11 point is what I meant to say. 11.16, right? Are we good? Now what? Natural log. Natural log so we can drop. So natural log e to the negative 4k minus 10 equals natural log of 11.16. And then we drop it, right? Bring this, drop it out. I'm putting it in parentheses because this natural log of e, that will always turn into a 1, but if that was not an e, then it would not turn into a 1. It would be a number like, if this problem had been, let's say, 2 right here, 2 raised to this power, then this natural log of 2 would not go away. You would have to use your calculator to figure out what that is. So that's why I keep this in parentheses. All right, over here, natural log of 11.16 is? 2.41. And then this is just 1. So negative 4k minus 10 equals 2.41. And now we're at the linear equation point, so we just try and solve for this k. I'll add 10 to both sides. Negative 4k equals, this side's 12.41. And then finally, divide both sides by negative 4. K is, let's see, 4 goes into 12 3 times. It's negative answer, 3. Goes into 4 once, and then I've got some change here. It's going to be 0.25, so I'll just go negative 3.1. Good enough. Does that help? We good? Yes?
So that negative doesn't really matter.
The negative what?
On the e, the race.
What about it?
Yeah, it doesn't really matter.
What negative?
You don't have to make it fun.
No. 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 Well, I'm not sure I understand your question.
Because it's like a negative exponent.
It's okay to have a negative exponent. Yeah, it's okay. Because, you know, if we said, we did this on our calculator when we were doing exponential functions, remember? We made the table if we were doing like x, and let's say 2 to the x, we were plugging in like negative 3, negative 2, right? So 2 to the negative 3 is actually a number. It's okay to take something and raise it to a negative. All right, let's move on. There's something else I want to talk about today. Let's do another word problem with money, right? And then I want to cover one more topic, and then let's see what time it is when I get through that, all right? So, what interest rate would you need to triple your money in 10 years? Question. And then this is, we are assuming simple interest. So you've got some money, right? And you want to put it into a simple interest account. And you want to know how long you want to know what interest rate, right? What interest rate would you need to have in order to triple your money in 10 years, all right? So let's first start with the formula, right, which is the shampoo formula. And let's talk about anything that we are given in this formula? Is there anything from that word problem that you know for sure? What? 10 years is what for us? Time, right? T. All right, so I know that much. T is 10. Right? Do I know the interest rate? No, but that's actually what I'd like to find, right? So I'm going to be solving for R. So the fact that R is there and R is the thing we want to know, that's actually okay. This is a smiley face, okay? So I'm okay with not knowing what R is because that's what I actually want to know, okay? Now, do we know what P is? I don't, do I? I don't know what P is. That's weird, right? I don't know what P is. Do I know what the amount is at the end? I don't. I don't, right? But here's what I do know. I do know I want to triple my money, right? Triple it. So if I put in P dollars, how much do I need at the end? 3 times P, right? So even though I don't know what A is, I can actually say that this is 3 times whatever I put in, because I'm trying to triple my money, right? If the word problem said double my money, I'd put a 2 here. If it said quadruple my money, I put a 4. Understand? Maybe we can still solve the problem by just knowing this. Let's rewrite the formula. Any questions on why I put 3P here? Triple money, we're good? Yes? Triple, 3 times as much? Good? Yes? P is the amount that we're starting with, even though I don't know what it is. It's something, right? All right, so watch. This equation becomes, this is 3P, isn't it? And this is P. I don't know what P is. E. Now this up here is R times 10, right? R times 10, which I'm going to write 10 times R, because we like to usually put the number in front of the variable instead of the number behind the variable. Is everybody clear on this? No questions? What are we trying to solve for? R. Okay, do you see where R is? Up in an exponent? Can you bring it down? There's a way to get it down, right? But we're going to have to work a little bit to get it down, right? We have the E that's being raised to that, right? We need to get that by itself. So how am I going to get that by itself? Divide both sides by P, right? P is just a number. Just imagine P is, that's how much money you put in. You don't know what it is, right? So who cares? Let's divide by P on both sides. And do y'all see what happens to it? It goes away. Completely goes away. Really interesting. 3 equals E to the 10R. With me? How do you get that 10R down now? Natural log on both sides. So I'll have natural log of 3 on the left side equals natural log of E to the 3R. Okay, so it's a little bit different than before. Like in the previous problems, this stuff was on the left side and the other stuff was on the right side, but it doesn't matter, right? It can be on the right or left. This can now drop in front. I have natural log 3 equals the 3R drops in front, then I have natural log of E, right? That turns into a 1. See, we're just doing the same thing we were doing before.
How did you get the 3R? Because you had 10.
Oh, wait, oh,
R
10.
turns to 3.
Good question. I have no idea how I did that. I'm just being goofy up here. Thank you for the looks on your faces could tell me something was wrong. Okay, sorry about that. That's just a mistake on my end. That's 10R. 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 My mistake. My mistake. Yeah. 10R, 10R, 10R comes down. 10R is in front. Natural log of E. All right. Now, on your calculator, natural log of 3. 1.098. And then equals 10R. One more step. Divide by 10. So divide by 10, and you get 0.1098 equals R. That's your interest rate written as a decimal. What is that as an actual percentage? 10.98%. You'd have to move this over 2 places. So as a percentage, your interest rate is 10.98%.
So whatever amount you put in for P, with that interest rate over 10 years, it will triple regardless.
Yes, so what's interesting about this problem is what it illustrates is that the amount of money you put in is completely independent of how much time it takes to actually triple your money. If I put $10, if I put $100 in here, right, for 10 years, as long as my interest rate is 10.98%, I will turn it into $300. If I put $1,000 in, it'll turn into $3,000. If I put $1 million in, it'll turn into $3 million. The amount is completely irrelevant, which is kind of interesting, right?
So you're saying a lottery winner should put their money into
Yeah, you put the money in, right? You invest your money, right? If you win the lottery, you invest that money because then it earns money for you, right? Because banks are lending it to other people who need it. Remember, we were talking about interest rates for credit cards, right? Like in the high teens, 20s. I mean, look at how much, this is 11%. Look at how quickly your money would triple. I mean, 10 years is 10 years, but I mean, you're tripling your money in 10 years, that interest rate. You could look at it backwards. If you borrowed money, right, at this interest rate on a credit card, if you don't make any payments, 10 years later, you owe 3 times as much as you borrowed, right? Okay. I want to talk about something else. So far, you know, this whole idea that the basic idea here is that we have introduced 2 types of functions, exponential, right, and log functions. Exponential and logarithmic functions. And we've learned how to graph both of those, right? And I think y'all would agree with me that graphing these is much easier than the other graphs we've done in the class, right? So we know how to graph these functions, but really, what's really been kind of useful and relevant to us is one of the applications, right? One of the applications of these concepts is the simple interest formula, and that we can work with this formula and actually solve for R or T if need be. We have a way of solving for the interest rate or the time depending on the problem, right? When I first introduced you to the formula, I always gave you R and gave you T, and I gave you the amount, and then I asked you, the P, and I asked you how much was left at the end, but that didn't require any of this. You didn't need any of this to do that. But now we have these tools, and now we can solve for those exponents. All right? So now what I'm going to do is I'm going to show you another application. This is called simple interest, right? I'm going to show you another application of those things, and that is something called carbon dating. Carbon dating. This isn't dating like going out with somebody you like dating, okay? This is, has anyone ever heard of this? So what is it? Can y'all describe it to your classmates? Like what you know about it? No? You heard about it.
Yeah, I mean, basically you're just trying to find the date of a certain object or an artifact of some form that's a long time ago, and you're using the atoms or carbon or something in that object to figure out whatever few carbon atoms you have left in there to figure out how old it is.
Exactly. That's pretty much it. I'll go into a little more detail, but that is the basic idea. So all living things, whether it be a human being, a cat, a tree, every living thing has something called carbon-14 in it. We all have it in our bodies, right? Carbon-14. All right, and carbon-14 is present in all of us. Our bodies naturally maintain a certain level of carbon-14, right? As soon as you die, your body no longer keeps that level up. So it starts to decay or deplete away. And it goes away and goes away, but it goes away exponential decay. So it's like, if this is a timeline, right, this is T, and this is the percent of carbon-14 in your body, or whatever living thing is, at time equals 0, time equals 0 would be when you die or this thing dies, all right? So when something dies, the clock starts. When they die, the amount of carbon-14 present there is 100%. So I'm just going to put 1 because 1 means 100%, right? Right? It does? 1, move the decimal 2 places to the right, that's 100%. So whatever dies, dies. At time equals 0, it has 100%. And then you get exponential decay. It starts to decay down like this, and it never actually goes to 0. I like to think about it like, it's hard for humans to put our heads around this idea, but I don't know if you've ever been camping before and ever built a real big bonfire, right? It gets like hot as shit, and you're like so hot you can't even get next to it, right? But if you come back the next day, right, it's burned out, it'll look like it's gone, but you poke your fingers in the coals, it's still hot, right? And it'll take a while for it to completely be gone. It's kind of the same thing with carbon-14. It's like you start off with everything, 100%, and then it starts to go away pretty quickly. But it's like a fire that never burns out. It just continues. You're always going to have a little bit of carbon-14 there. So what we do in science and archaeologists and stuff, they find like a bone, right? They take it to the lab and they measure how much carbon-14 they find in the bone. So maybe they take a measurement and they say, hey, we found this much carbon-14 right here, whatever this number is, okay? That's how much they find. And then from that number, they can actually go over to the graph and come down here and they can figure out how old the bone is, all right? By just knowing the percentage of carbon-14, they can determine how much or how long that thing has been dead, right? That's the idea. Got it? All right, so this idea of carbon-14 dating, or it's called carbon dating, is a specific example of what's called half-lives. So have y'all heard of Half-Life before? Not the video game, but you've heard of Half-Life, yes? What's that?
Like medicines?
Yeah, in medicines. So like if you take ibuprofen right now, right? Ibuprofen, you have a headache, whatever, muscle ache, you take an ibuprofen, that gets into your bloodstream, and you have ibuprofen in your bloodstream, and then it starts to, eventually, like the next day, it's not there as much, right? 4 hours later, it drops off. All medications have that same sort of idea. You put the medicine in, and then whoosh, it drops off. How fast it drops off depends on the medication. Some medications, the drop-off is very quick. Some medications, it stays in your body for a long, long time, right? Do you have a question?
Is that sort of like with radiation?
This is exactly like, so
Like
this
Chernobyl, right?
Chernobyl, any radioactive materials have half-lives. So let's talk about what a half-life is, all right? Because this is important for us. Because a lot of you have heard of what a half-life is, but now I'm going to show it to you. We've done this example before, all right? So let's say, what do y'all want to use? Ibuprofen? Yeah. Let's do ibuprofen for right now. Okay? So this is I take ibuprofen. This represents how much ibuprofen is in my bloodstream, okay? For ibuprofen, there is a known amount of time. We've calculated it